Welcome back to the PLC Professor's Workshop and Lab. As you can see, the equipment behind me, this is where I sort out all of my lab projects. And I'm assuming that you've done part one, semester one of Connected Components Workbench with the Micro 800. This is semester two, part two. Some of these lab projects are not very complicated, but all of my lab projects are meant to demonstrate certain characteristics and behaviors of either PLCs in general or specifically the platform that we're working with. Now this is Micro 800, and actually at this point it's more about programming techniques, logic techniques, than it is about the Micro 800. And as you also might know, that out of the, we'll call it the three platforms that I teach out of for controllers, RS Logix 500, RS Logix Studio 5000, and now Connected Components Workbench, that I tend to use the exact same logical projects or logical demonstrations to demonstrate the characteristics and behaviors of the software and the hardware. This particular lecture discussion is for lab project M17, which is the first or second lab project in the second semester. The first lab project currently is the three compressors, which is where we introduce heavily the option for the simulator of doing a configuration of I/O wiring, and also multiple programs, and I introduce a little bit more effective HMI in the sense of having a program that you can monitor on the screen. You're looking at logic, rungs of logic, but what's viewed in the rungs is more about the information than about control. And these rungs typically have a no operation coil at the end, or a no-op instruction if you like that better. So now we're going to start doing the projects in M17. So let's start looking at them. This lab project can be found in either one of these two manuals. It's not going to be found in part two of the first edition, but it is found in the second edition and the third edition. Keep in mind, if you have the second edition, that's good, but you can no longer buy the second edition of the manuals, just the third edition. So if you're watching this video without having the manuals, you're looking for the second manual there, part two, third edition. We're going to start out with the second piece of logic in M17. The first couple of rungs that we did were extremely simple, don't take any explanation. They're just too simple to require words to explain them. This is a little bit different. Now you notice that I'm online, and notice that none of the I/O are on. So if you look over here at our simulator, you see 0 through 27, they're all off, and output 0 through 19, they're all off. Okay? Now, my first question would be, could this cylinder be in the state that it's in? And what do you mean by state? Well, output 1 and 2 are off. We have no solenoids energized. The other two elements would be the input 1 and input 2, cylinder extended and retracted switches. Now remember that with Connected Components Workbench, the text, which is the memory location above the instructions, you can tell whether that's on or off by the color. So if it's blue, it's off. If it's red, it's on. Instructions are true or false. Memory locations are on or off. So we have 5 true if off instructions there, and they're all red. That's because all their memory locations are off. So true if off. Well, can input 1 and input 2 both be on at the same time? Can the cylinder be in the retracted and the extended state simultaneously? Of course not. But can both of those inputs or position switches be off simultaneously? Of course. If the piston is in motion or stalled anywhere in between extended and retracted, then both of these instructions are going to be true because both of their switches, input 1 and 2, are both off. So let's start with this thing in the retracted position, which means that I need to turn on input 2 here. So let's go over here to the simulator and turn on input 2. Now you see this went false. Now, so what you should see immediately is that we can energize the extend solenoid and extend the cylinder position because it's not already extended. But we can't retract it because it's already retracted. Also notice that you don't see the full simulator on the screen. Okay, I pull it over here so you can see the whole thing, but we don't need to see the whole thing because we're only going to use the first couple of I/O points on it. And I see that there's still some I/O wiring here from a previous project, so I'm going to pause and delete that and come back. First I'll show it to you. Device, configure I/O wiring. This is for another project, so I'm going to cancel that. I'm going to pause, clear out that I/O wiring, and then come back before I start operating our project. And the reason that I'm leaving this in the discussion is because this is easy to do, is to leave this configured I/O wiring from other projects when you go on to new projects. So you always need to remember to clear that before you go to the next project. Okay, I've cleared that configure I/O wiring. You see it's empty now. And you might think that you could go up here to this button, synchronize the module configuration, and it would also clear the I/O wiring table, but it does not. You actually have to go into the I/O wiring table, and of course there's nothing to select now. Select one of these, and you have to do this when this is not powered up. If you got this device powered up, you can't delete the I/O wiring table. So this has to be not powered up, this simulator. You can select the top one and just keep hitting the delete button until they're all gone. But you may want to save it before you delete anything, and you can export it and give it a name. That way if you go back to that project, you can import it back in and you've got all that work saved and imported back in. So if you're going to do configuration of I/O wiring, once it's working the way you want, export it with a name that you'll recognize, and then when you go to a new project, delete all of the I/O wiring table before you get into that project. Okay, now looking at this. Now that I/O wiring did not interfere with what we were doing. I just happened to notice it, and it's not ordinarily what I would do. Now, if I make mistakes, there's a good chance that some of you might make mistakes. So some mistakes I leave in the discussion and they tell you how I deal with it. Other mistakes, if there's no learning experience, I delete them out of the discussion. Okay, here we go. So let's put this into the retracted position, and you can see now that we can extend it. Let me just say this. In this position, neither extended or retracted, I could go either way with the operation of the cylinder. But let's do it the way we did it in the manual. So we turn on input 2 because it's retracted. Now, if I say cycle once, initiate cycle, because it's already retracted. This is a pulse rising instruction, meaning when this bit went on, this instruction went true for one cycle. So it can't go true now. I mean, it went true when I first went into the run mode, and it can't go true again until this input 2 goes off and back on again, meaning that the cylinder has cycled. So let's initiate a cycle by right-clicking on initiate cycle, toggle bit. Okay, so I turn this on and I reset this bit. Now this is typical logic. At least I do this a lot. If I'm going to toggle bits with my mouse, I'm probably going to include a reset coil in the end of the rung to make it a momentary initiate cycle. In other words, if I toggle this on, it'll stay on unless something else turns it off. So I'm using my logic to turn it off so I don't have to double toggle it on, toggle it off. Okay, so now we have cycle once state initialized. Okay, cycle cylinder once is on. If we look at these two rungs here, we see each rung has an instruction that's false. This one is false because the cylinder is retracted. Well, the only way we could legitimately get this instruction to go true is if we were to extend the piston and pull it off of input 2 so input 2 could go off, and then we could retract it. However, we have to extend it first. So I'm going to turn on input 0 to extend it. So go over here to simulator, click on that. Okay, extend cylinder A. Now what should happen the instant that cylinder A starts extending? Input 2 should go off, right? Because you've pulled it off of that position. So we turn off input 2 and the cylinder is still extending. Now let's turn on input 1 saying that it extended. So we turn on input 1 and now you see that it's neither extending or retracting. Okay, it's extended. Right now it's stationary, it's extended. Now notice that we're operating the solenoids. If this were spring return to center, double solenoid, then right now the solenoid would have, the valve spool would have gone back to the center position, so it's not porting the pressure to either side of the cylinder. Let's not get too complicated. Let's just say that right now you look at the sensors to tell you where the piston is at. Input 1 is on, extended. Input 2 is retracted, is off. So right now it is extended. And if you look at your logic, in order to do anything, we either have to turn off input 1, which we can't do without moving the piston, or we have to let go of the extended cylinder push button. Now I have it as a push button, which means that all this time I've been holding my finger on input 0. Now if you're using real hardware and a digital field device simulator, especially if you're using the ones that we design, then for input 0 you have a toggle switch so you can have maintained on, maintained off. But you also have a push button that's wired in with the toggle switch, so you could use input 0 as a normally open or a normally closed. So I'm holding my finger on input 0 right now in a sense, even though we're using a simulator. So I have to let go of input 0. But when I do, this instruction is going to go false and this one's going to go true, not the bit. The bit right now, you see, it's the same bit, it's on, but this instruction is true, this one's false. So let me turn off input 0, and now you see we retract cylinder A. That rung is now true. Now what would happen the instant that you retracted cylinder A? What would happen to the extend switch? That would go off, right? So we'll turn that off. So technically, the piston in the cylinder is in between extended and retracted. See, these are both off. Both instructions are true. They're both off. And we are retracting cylinder A. And we will retract it until input 2 sees the piston in the retracted position. Let's turn on input 2. Okay, notice that when input 2 went from false to true, retracted switch, this pulse rising instruction, contact, was true and it reset cycle cylinder once. Now, if I put on input 0, nothing's going to happen. In other words, this is logic that allows you to cycle the cylinder once. Is this real practical logic? Not really. We're trying to demonstrate, or we are demonstrating for your learning experience, the behavior of a set coil, reset coil, and a pulse rising contact, as well as the idea of two levels of logic. The initiate cycle cycle cylinder once. So the first rung and the last rung, that is one level of logic, and then nested below that, dependent on the first and the fourth rung, is the two rungs that are enabled by cycle cylinder once. Although I did answer all of the questions that are in the manual, there is one spot where I will kind of review or reiterate, and that is where it said, before initializing a cycle, what state should the following be in? Cycle cylinder once bit. This is before you initialize the cycle. Cycle cylinder once bit should be as you see it right now, off. Cylinder A extended switch should be off. Cylinder A retracted switch should be on. Extend cylinder push button should be off. Extend cylinder A solenoid should be off. And retract cylinder A solenoid should be off. Then I said, beginning with the first step, list them all in order with variable names. So first of all, it didn't ask, well, it did. This one has to be on and this one has to be off, okay? So the first thing we do is we initiate a cycle. The second thing we have to do is to hit the button to extend it. So we have to go up here and turn on input 0. It's extending. So we're going to turn off the retract switch next, off with 2, and then eventually on with 1. Okay, so now it's extended. To get it to retract, the first thing we do is we turn off input 0. Notice we let go of the extend button, and we turn off input 1 because that's the extended switch, and then we turn on input 2. That's the retracted switch. And then it will automatically reset itself. So when input 2 goes from off to on, false to true transition on this instruction, that's pulse rising, this rung is true for one program scan and resets cycle cylinder once. Now the only thing I didn't mention maybe is that when you toggled on initiate cycle, that was step 1, and step 2 is that it turns itself off when it sets cycle cylinder once. So if you want to include that in that sequence, that's your business. This is the last piece of code in the lab project M17, and it's getting closer to what we want to end up with, where we have less interaction with the code. For example, here we have a dual solenoid or double solenoid valve, which the two solenoids are controlled by output 1 and output 2, extend and retract. And we have two sensors, input 6 and input 7. Cylinder 1 extended, proc switch, and cylinder 1 retracted, proc switch. Also in our view here, I have the global variables up so you can see that the logical value is checked for cylinder 1 retracted. I'm going to operate this, and I operate it solely with input 0. So in the previous code, I had to manually toggle inputs on and off to simulate the behavior of the cylinder position, the state of the cylinder position, or rather the piston inside the cylinder. So I'm going to turn on input 0, and you can see that the extend solenoid comes on, and after 2 seconds, it turns on input 6. And you see down here, 7 was on, now 6 is on. If I turn off 0, you can see that it goes through a time delay. And during that time delay, neither of these two inputs are on. Now it shows input 7. Now you may be thinking, well, wait a minute, we're running. Why isn't the controller overriding my inputs? Well, remember, these are buffered. If we were using the real inputs, and I will scroll down to some of those. There we go, digital input 6 and 7 right there. See, neither one of them is checked. Notice there's a logical value and a physical value. So as I turn this on, you can see nothing's happening except digital input 0, which I clicked on the simulator. It shows it's checked. It also shows the physical value checked. Now remember that the physical value, and if you haven't watched that lecture, you need to watch it. It was part of semester 1. The physical value is implying that that is the state of the screw terminal. And of course, whether or not it is a screw terminal would be determined on whether or not this was in the run mode or the program mode. In the program mode, when you switch to the program mode, you may lose the screw terminal. I mean, the screw terminal is going to stay the same for an input, but you're no longer updating this memory location right here, okay? This may stay the same when you go to the program mode, because this value, physical value, is going to be the last state that it saw. So you never want to depend on the physical value being what the screw terminal is if you're in the program mode, because if you go to the program mode and then you change the state of the screw terminal, which you can do that with real hardware, you can't do that with a simulator, then all bets are off. Okay, looking at this code, I've got the extend cylinder push button pushed right now. Hold my finger on it, and it extended, and then 2 seconds after I turned on the solenoid, it turned on input 6. That's simulating our extended cylinder proc switch. So I'm going to turn off 0. You'll see that this is going to go off immediately, and then you're going to start a time delay of 2 seconds, after which it's retracted and turns on input 7. Nice little piece of code. And you are only turning on and off input 0. So you're controlling it with a single push button. It could be a switch, a toggle switch, and you toggle it on to extend, and then you rotate it back to the off, maintain toggle switch. Either one will work. So that takes care of Lab Project M17, and you'll see some of this code again. If we were doing this with the device configure IO wiring, then we would take output 1 here and attach it to input 6 here, and we put in a delay of 2 seconds, and we get the exact same behavior. Play with this until you're bored with it.